Our introduction to kinematics is basically just how can we describe the motion of objects. So we're going to do that with words. We're going to do that with some equations. Eventually, we'll be doing that with some graphs. So as we go through and do these, that's kind of the overview, the main questions we're going to be having, describing, calculating, graphing the motions of objects that we have. So some of the vocabulary we're going to have is distance, displacement, speed, which can be either instantaneous or average, velocity, and then 2 words, scalar and vector. So you see those, if you're taking a note along with this, those are the ones that you probably want to key in on. So 2 of the words are distance and displacement. Both of these are similar to one another, and they're both measures of length. So it's how far something is from one another. In physics, in everyday language, you probably don't use these that much different. But kind of an example would be if when I'm driving to school in the morning, my distance here, say is like 25 miles, which means my distance back home is also 20 miles. So at the end of the day, I've driven to school and I'm going back home. My distance is what's showing up on the odometer of my car. It's like 50 miles is how much my car has traveled. Displacement's a little bit different though, because displacement is simply how far am I from when I started. So when I get to school, my displacement's probably 25 miles, but when I get back home, my displacement is 0. So even though I've traveled 50 miles of distance, my displacement is 0 because I'm right back where I started from. You may think this is a little bit silly, but in terms of some of the mathematics that we use, there's a distinction between these two is kind of important. But the real difference is that distance is a total length, like with my car, is that I've gone 50 miles. My car is not going to go back to 0 when I go back home. It's not going to subtract the distance off. Displacement actually does that. So if an object moves from point A to point B, it has been displaced. But if it moves from point B back to point A, then it's back where it started from. And technically, it hasn't gone anywhere. It's back where we started from. So it's kind of a before and after, and not just kind of a total measurement of how far something went. Because these are measurements, we tend to use a couple of different units here in the United States. We use inches, feet, yards, and miles. However, this is a science class, so we tend to use the metric system. So we got meters, centimeters, and kilometers. A couple of new vocabulary words to you probably are scalar and vector. Some measurements are scalar measurements. Some measurements are vector measurements. Scalar is a simple measurement. Vector makes it a little bit more complicated. Scalar means that it's just got magnitude only. So an example of that would be like 2 miles, 10 centimeters. To understand how a vector is different, a vector is going to have a direction to it. So instead of 2 miles, I would need to say 2 miles north, or 2 miles up, or 2 miles positive. I need to give it some kind of a directional quality to make it a vector. And again, 10 centimeters would be scalar distance. 10 centimeters west would be a vector distance because it's telling me the exact direction of which to go. Throughout physics, one of the things we tend to do to illustrate vectors is we use arrows to indicate a magnitude. And so a lot of times what we can do is we can use the size of an arrow to indicate the magnitude of something. And we can use obviously the direction to be able to tell which way it's going to be going. For some reason, I'm not able to draw. So I guess I won't draw right now. If we wanted to draw, if we had an up arrow, that might indicate north or up or positive direction. If the arrow was longer, that would tend to indicate a larger magnitude than a smaller arrow would. So if you wanted to illustrate a bigger force, you would draw the arrow longer, and then the direction that it's pointing would tell us which way the force or the direction is going. When we're doing speed, by definition, speed is a rate of change of motion. What that really means mathematically is it tells me something about the distance and time. So when you're calculating the speed of your car, what you're doing is it is a measure of how much distance is it covering each unit of second. So in a car, we say miles per hour. That's our distance divided by time. So the greater the speed, the greater the distance we're covering each hour. A car going 60 miles per hour is going to go farther in the same amount of time than a car going 50 miles an hour. And if you're running a meters per second, faster you run, you're covering a greater distance in the same amount of time. Likewise, 2 people who were running and racing, they would cover the same distance, but the faster one would do it in a less amount of time, which makes them mathematically going faster. Instantaneous is the speed at one moment in time. Apologize for the typo. So at that instant. Now, technically, it's impossible to measure an instantaneous velocity without it still technically being an average velocity, because an average velocity needs to take two velocities and figure out what is the kind of average during that. So it's going to take the total distance traveled divided by the total time. When a policeman's doing a radar gun or a laser gun and finding someone's instantaneous velocity, it still is an average velocity, but it's an average velocity over an incredibly short amount of time so that they can figure out how fast are you going at that moment. Right? When we measure speed, if we went 5 meters in 5 seconds, that would be 5 meters divided by 5 seconds. So we get an answer of 1 meter per 1 second, or 1 meter per second. If we triple the distance in the same amount of time, we're going faster. So if we cover 15 meters in 5 seconds, then our speed is going to be 3 meters per second. Notice I have numbers and I have units after them. Again, these are going to be scalar measurements because they don't include a direction. They just tell us how fast we're going. If you looked at something like this piece of paper, and if an object was moving and it was dropping a dot at the same amount of time, I'll say that these dots were dropped every second, and you're asked which one of these two would be going faster, or are they going the same speed? The one at the top would be going slower because every 1 second it's only traveling this distance that my arrow is showing. The one on the bottom, every 1 second is traveling a greater distance. Therefore, since the distance is greater and the amount of time is the same, the one on the bottom would be illustrating something that would be moving faster. So the idea is if we were dropping dots at a constant rate, the farther they get spread out, that would be an indication of something going faster. Things that were close together wouldn't be going very fast at all. Velocity is very similar to speed. In fact, in the English language, we use the two interchangeably, but velocity replaces distance with the word displacement. Notice it's a very subtle change, but remember, displacement has a direction to it, right? And so this is the difference between velocity and speed. They're both measures kind of how fast something is going, but velocity takes direction into account. So a lot of times mathematically, there's a really small difference. It's still 300 kilometers, which is a distance, and it's 10 hours, which is a time, but we're going to throw in this direction component. So anytime you're being asked about velocity, your answer needs to have some kind of a direction to it: north, south, east, west, up, down, positive, negative, left, right, something along those lines. Therefore, this is a vector measurement. Mathematically, you don't do anything different. It's still the distance and the time divided by one another, but technically it's the displacement divided by the time and not the velocity. Finally, one of the things we can do with the velocity formula or the speed formula is to be able to rearrange it. We did this in chemistry a lot last year with some of our formulas. Distance is speed divided, speed times time. Normally we say speed is distance divided by time, which is the one that we have on the bottom. So if speed is distance over time, we can turn that into our triangle by putting the speed over here on the left. Since distance is at the top of the fraction, it goes at the top of the triangle. And therefore, speed and time tend to be on the bottom of the fraction. So if we want to solve for distance, we can kind of cover up the d. And we've got the s and the t side by side, which tells us that we need to multiply them. If you're trying to figure out the amount of time something takes, then we take the distance and divide it by the speed. And that would give us an idea of how long it took to get somewhere if we knew how fast it was going. And then again, at the very end, to calculate the speed, we need to know the distance and we need to know the time.